Hi everyone, welcome to Adventures in Extending miniKanren. I'm excited to present this talk here. This is joint work with Michael Valentine and William Berg. So what we'll see today is three things really. One is stageminicameron, which adds multi-stage programming to miniKanren. The other is CLP SMT miniKanren, which adds SMT solving to miniKanren. And we'll look at an extension pattern that applies to both these projects in terms of how to extend miniKanren with extra things in the state object. And a few other things we'll learn along the way is turning interpreters into compilers, learning about SMT solving, and we'll see immediately now an application to synthesis. Here we have the Fibonacci function and accumulator passing style. And what this means is that we have two extra arguments for the accumulators A1 and A2. And once we reach 0 for n, we return A1. Once we reach 1, we return A2. And then we increment these as A1 becomes A2 and A2 becomes A1 plus A2. And we subtract 1 from n every time we loop around. So then we can call fib with the accumulators 0 and 1 to get the Fibonacci sequence. And now we can think of these examples here as test cases. And we can ask a synthesis question, which is, given the skeleton of Fibonacci, can we actually infer the step 1 and step 2? And can we infer the accumulators like 1 and like 2. So what we would like is to obtain the code at the top, given the holes here at the bottom. And there is a catch though, again, which is that we would actually have to write it this way. So instead of writing Fibonacci 0, 1, we should use piano numbers. It doesn't change the main Fibonacci function because 0, sub, and plus can deal with piano numbers instead of dealing with regular numbers. And then here we have Z for 0 and S of Z for successor of 0. So for example, 3 is S of S of S of Z. And so we can use the same problem, but this time not using built-in numbers, but using piano numbers because we don't have that feature in miniKanren. Okay, so how are we going to solve this problem? So let's look first at a Barleman solution, which looks like this. So it takes about 8 seconds of CPU time. And here we're giving the skeleton. And then we're saying A and B are unknown. These are the steps. And then we're also using fibabs on the actual examples. And we're giving unknown accumulators. And then we give the result here for this, the Fibonacci sequence. And finally, what we get as a result is the code and the accumulators. And that's because if we look at the top here, we have the definition of the accumulators. So that's what happens, and it takes 8 seconds to run. Now let's see if we can do better. So we will look at staging in a bit, but the staging solution is basically that we define a stage relation with our steps and our accumulators. And then we write this in a similar fashion where we have holes for the steps and the accumulators. And that's just the staging function. So we create a relation for that. And then we apply the relation on unknown steps and unknown accumulators and with the actual output we were looking for. And we get the actual synthesized snippets. And so this runs the staging relation itself runs in 0.05 seconds, and the actual synthesis runs in 0.5 seconds. So that's a huge speed up, and not all problems are like that. So there are some problems where Barliman does better, but they're doing different things. So Barliman has a lot of handcrafted optimizations, while the stage interpreter is a principled sort of interpreter turned into compiler approach, and using the interpreter from the faster miniKanren repository. So we'll come back to that, of course, and then finally we can see the version of this using CLP SMT. So here we have actually added true numbers in the interpreter, and these 0 sub n functions work on numbers. And here we have the input cases and the output sequence, and here we have the skeleton result. So sorry, here we have the skeleton result, and here we have the actual result. So what we see here is this is actually quite slow. It's 32 seconds of CPU time. And the reason is that it keeps calling the solver to solve these arithmetic operations. So there's future work to do to make this faster, but it's still neat that we can write this directly using numbers. And just to give other examples of numbers we have in the system, we have here, so say 3 plus 4 is equal to 7, and things like that. So yeah, that's it for the introductory example. So what we've seen is that we have this Fibonacci function, and then we give it as a synthesis problem. So given this, the first 5 Fibonacci numbers, or 6 rather, can we synthesize the step and the accumulator? And we can in 3 different ways with different performance. But that's interesting that we can do that. Let's look at the basics of stageminicameron. So recall in miniKanren, if you run a query with a unification, the unification happens right there. So I get a 1, and that is the possible answer for Q. Now, if I run the same query, but use a deferred unification instead, so later ln, later equal, then what I get is that Q is unbound, and then after the bang, I get code that says that Q unifies with 1. So just to play with this a little bit, this is a pretty simple facility. It doesn't do any simplification. So if I do list1 equal list Q, then I get these const pairs here, even though they're not necessarily. We just want to unify 1 with Q. And similarly, if I do 1 equals 2, then that would fail as a normal query. But as a staged query, we defer the failure to the second stage. And we can use the later operator directly. So run stars Q L equals Q1 is the same as run stars Q later equals expand Q expand 1. Okay, and now we can do a more interesting thing with a staged operation. So run staged runs the query in 2 stages. First, it does it generates the data code, and then it runs the data code. So if I do Q1, I get 1 because it's running the first stage and finding something that looks like this. And then it's running the second stage and then this returns 1. So run stage forces the code in the first stage to be deterministic. So if I did something like and that returns an error because the staging is non-deterministic. There are 2 possible results during staging time. However, I can use a later code explicitly to do that. So if I wanted to actually have a conditional in the generated code, I could do and then I get the result 1, 2. So that's the basics of stageminicameron. We're not showing anything here that has to do with the interpreter and with evaluate. These are really the primitives that you can find in miniKanren. So this in stageminicameron. So this add equal, this later operator, which is more general, and this run staged form, which allows you to run a query in 2 stages. If we write a relational interpreter in miniKanren, we can turn functions into relations. So for example, we might have a proof checker that we turn into a theorem prover. And if we stage the interpreter, again in miniKanren, we can then turn this proof function directly into a proof relation without the overhead of the interpreter. And in general, we can turn interpreters into compilers. So the idea is that an interpreter is something that takes code and additional input and produces a result. And staging is a process that produces code. And by staging an interpreter, which takes code and some symbolic input, we can generate second stage code that when executed with actual input produces a result. And so going back to our picture here, what we see is that the stage interpreter is a compiler from a functional code to relational code. So it turns functions into relation via compilation. Now let's look at some examples that involve the staged interpreter, evaluate staged. And here's an example where we have defined the map function to be in the context. And then we do map lambda x with some unknown code here on ABC, and we get the output A.A, B.B, C.C. So intuitively, we know what must go here. It should be the constant of x to x. So let's run it and see what happens. And we get indeed const xx. And if we run it in the unstaged evaluator, we would also get the same thing. So the difference here is that we use run stage, evaluate stage versus run and evaluate unstage. So now let's define a stage relation, which we define it using a function and turn it into a relation. So here we have the append scheme function, and then we turn it into a relation using evaluate staged, where we give the inputs xs and ys, and we get the result zs. So let's define this, and this is how long it took to stage this function, so not very much. And now we can call it like the regular appendo function, and it behaves exactly in the same way. And in fact, if we look at the generated code, it's pretty much the code that you would write by hand, modulo these constraints that come from the interpreter, which we can't ignore for for correctness, just to match the interpreter semantics. So let's take a look. So that's what it looks like. These are the constraints. Apart from these constraints, we see that we have low-level code that matches against the result to get the appendo. So here we see that if we have the empty list versus if we don't have the empty list, and so forth. So we can see that it has compiled away the interpreter loop. Let's look at a bigger example taken from the ICF paper 2017. Here we have a functional evaluator that understands quasi-quotes, and it's running inside the relational interpreter, here the stage relational interpreter. And so what we get is a relational interpreter for that handles quasi-quotes. In the original Perl, that had the overhead of the base relational interpreter. But here, because we're using eval stage, we're actually turning this eval quasi function into a relation without much overhead. So let's see what happens then if we run this code. So it still takes a while because it's doing this client search, and here we don't have the luxury of Barleyman's optimizations, but it's much faster than the equivalent original program. Okay, so it returned this expression, which is indeed, if we look at it, is indeed self-evaluating. So that's good. And then in general, what we can say about our staged interpreter is that run stage, evaluate stage should produce the same result as run evaluate stage, modulo something, so modulo errors, because the stage interpreter might catch errors early, modulo the answer order, and modulo the representation of closures, because the closures in the stage interpreter contains stage code as well as no stage code, respectively. Let's now look at the stage interpreter. In the same way that the relational interpreter is a miniKanren program, the stage relational interpreter is a stage miniKanren program. And the idea is that we have the expression, which should be more or less known. And if it's known, we can generate code that is specific to that expression. However, we want to make sure that we only generate one answer. So if the expression is unknown, we want to fall back and generate code that calls the on-stage interpreter here. So for example, here we check that if expression is a variable, then we generate this call to the on-stage interpreter. So we will have explicit calls in the generated code in places where we don't know what the expression is. Now, if we know what the expression is, then we can dispatch on it as we do in the normal interpreter. So if we have a number, then we return we unify the expression and the value in the second stage. So using this later to construct an equal. And I'll come back to the staged parameter here. Well, let me just tell you right ahead, we use it so that we can do the inlining for closures. So when we have a closure and we know exactly which closure we're talking about by using stage false here, then we can just actually apply it by extending the body as we usually do. Now, the rest of the stage code is referring to the case where we have a rater and rans. And that's, now we have to consolidate the cases that are in the normal interpreter because we want to make sure that there's only one deterministic answer. So for example, here we check that the runs have a ground spine. Otherwise, you have a way to go non-deterministic. Or here, we check that the parameters are ground. So that's the basic of it. Just to give some idea, I'm going to show the if primo expression. So here, if primo actually is a little bit more involved, because what happens is that we have those branches and we want to make sure that each branch stays within its own scope. So that's what later scope does. It ensures that that when we call this goal here, we put everything that the goal generates in C2, and then we ignore everything that was recorded, like the state object that was recorded for the later scope. And then we can generate a condi with C2 and C3. Maybe let's look at another case. Which case would be interesting? So let's see. So let's look at car, for example. So here we just unify in the second stage the resulting val that we care about and the argument to the car once evaluated. And then we make sure that val is not a special tag. So if we look at the node tag rule, these are the special tags that we use in our interpreter, so we don't want them to be also used by the user directly. So just to recap, we have this eval expo, which takes whether we want to stage right now or not, and then the expression, environment, and value as usual. And then we assume that the expression is mostly known. This is what we're going to be staging for. But if it's not known, we manage to also handle this case by using later calls to ueval expo here. And just to show as well how closures are handled. So here, if we have a procedure, we have the rater that we saw earlier, and then we evaluate to a procedure. And here we put false for the staged parameter because we want to know exactly what this procedure is. And if we get a closure here, then we can start evaluating the body. And if we get other things like if we get a prim for a primitive, then we also can evaluate it as a primitive and so forth. Hopefully that gives you an idea of the stage interpreter. Let's look at some benchmarks now. First, I will describe the column. So staging is the time it takes to run the first stage, so to get the generated code. Staged is the time it takes to run the second stage, so to run the generated code. Run stage is when we lump the first stage and second stage together in the run stage form that we've seen. And unstaged is when running the completely unstaged version of the code. And of course, the gain is comparing the unstaged version to either run stage or staged. Okay, so we see substantial gains here. And sometimes the unstaged code times out after 5 minutes. And so we can calculate a minimum ballpark gain. And here for this synthesis of fib, which we've seen earlier, one of them, we see a huge difference in the staged and non-staged behavior. Okay, so let's describe the benchmarks in more details. So first, parse is for parsing with derivatives. And what the relation does is that it takes a regular expression, a token, and produces the derivative of the regular expression with respect to this token, which means what would the regular expression looks like after we consume the token. And the parse backwards means that we set the initial regular expression to be unknown, and we find it by reversing the derivative. And proofo is our theorem checker turned prover. And we see that for bigger problems, the unstaged version times out. NFF stands for negated normal forms. So here we see that the gains are good, but not substantial still compared to the others. And then here we have the piano fib examples. Let's take a look at CLP SMT from a user's point of view. So we're using logic programming or relational programming, and we're hooking it to an SMT solver. So what we have here is assertions that go to the SMT solver. So here we're saying the variable Q is greater than 0, and it's also less than 2. So mathematically, it has to be 1. And here we're saying we have 2 variables, and they sort of fall into this pattern where they're both greater than 0, and then x is equal to y plus 1. So if we run this for 3 answers, we get 3 answers here. And we can also use Condi. So the point is that miniKanren does the search, and the SMT does the constraint solving. So here we have 2 answers because we have 2 branches. And yeah. And now let's look at factorial. So factorial is using SMT solvers is a lot of asserts to the SMT solver. And here the recursion is done by miniKanren. So we're unfolding the computation, we're unfolding the request to the SMT solver. Okay, so here we get all the factorial numbers. And that takes a little bit. And then we can also do factorial backwards. And here, 6. And now we can have an evaluate interpreter, a relational interpreter that understands integer operations, so like plus. And here we have factorial written as a function, and we can do the same tricks because evaluate turns functions into relations. So here we can run it backwards. And here, this is running, sorry, this was running forward, and now we're running it backwards. Okay, so we get 6. And now here, we make sure that we quote the result so that we don't get miniKanren operations. Like here, if I did 2, I would get miniKanren operations. See, so quoted 6, and I could get more, but let's just leave it at that. And here we can run it with the quotes so that we can test if there are more answers than one. Okay, and we get just 6. And here we can do a little bit of symbolic execution. So we say that the result is bar. So what should Q be here? If the result is bar, so Q should be anything but 137, and that's what we get. So it has picked, okay, so here it's picking different number as the one in the solution, but they're all not 137. And here we can ask similarly, if we get the answer foo, what should this be? And we get this number here. Okay, and now we can do a little bit of synthesis where we have this operation here and these two expressions. So we're giving it a template for what things should look like. It should look like this or like that. And then we're looking for F. And so F should satisfy that F1, F2, F3 is equal to 2, 4. Sorry, F1 and F2 is equal to 2, 4. So if we run this, we get true, and these were the results. So yeah. Okay, so this is what I wanted to show you. And yeah, so one thing we'll do now is look under the hood of this. So here is the SMT log generated for the query FACO backwards 2. So just asking what is the number such that the factorial of this number is 2. And notice that we do a run star and we get only one answer. And here is the query which succeeds in giving one answer. So we see that it has unrolled the loop. So first it went on the second branch, and then finally at the end it goes to the first branch, and so forth. So let's look at the model generated for this because it's satisfiable. So we get the model where the variable 0 is 2, the variable 2 is 1, 1 is 1, and 3 is 0, and 4 is 1. And the one we care about, of course, is the variable 0 here. And what we can see is how does the run star itself work? Well, if we look at the last query that the SMT solver did, then we see that it has this extra clause here that says we want an answer that is not the previous answer, matching the model here. And we see that this is then unsatisfiable, so we know that we're done with all answers. So that's in a gist how the SMT solver works in the context of miniKanren. So miniKanren does the search, does the high level arguments, and then it unfolds everything and sends it to a solver. So let's see how we can augment the state with extra information. And we will do this in fastminicameron, originally written by Michael Ballantyne. And it's pretty similar in canonical miniKanren. It's just that fastminicameron is faster, so we might as well use that. And so here, the original representation of a state in fastminicameron is a substitution and a constraint store. And what we do is we augment it with an M for extra things we want to store in there. And we change the interface from a const to a list of 3 elements. And so we have to propagate those changes, and there aren't that many of them. And that's basically what we need to start the pattern. Then we can see how to implement a log extension. So all it does is that it logs extra stuff on the successful branch. So here, for example, we have log hello, log world, and we get hello world. Or we can log into different branches and we get the logs into different branches here, different answers. And here we can have appendo that logs B every time it takes a recursive step and A for the base case, and we see that we get B, 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 A. So how do we implement this? Well, it's a simple thing, really. It's just this log thing takes a line, and then it's a goal. So it takes a state and returns a state. And we say it's the state that modifies M, and it modifies M such that the line is added to the state M. And this is something we had defined here, state with M. So it gives the substitution and the constraints to unchanged and modifies M. And then finally, for reification, to be able to see the result of the logging here, we actually, when we walk the final thing to reify, we actually check if M is non-null to return the M as well after a column. So that's all there is to this very simple extension, but this is basically what the pattern is about. It's about extending the miniKanren implementation to have extra information. And this is just a mechanical interface change. And then it's doing things that are specific to the extension. So here, this logging function, and then this reification for the logging. Now let's take a look at the implementation of stageminicameron and see how it fits the pattern that we've just described. So here the later construct takes something, and then it's a goal, so it takes the state, and it creates a new state. And the last thing in the new state is what we've just added as code, and then the rest of the code here. So we're just accumulating code in this in our state object in order to do staging. Now later scope, which you've seen for handling branches, like the if branches in the staged interpreter, what it does is that it's basically calls a goal, this goal here, on a new state with a new layer of constraints that are generated, and then it generates the constraints, and then it basically ignores all the state that was used and generates and gives back the original state. And in the meantime, it sets this out variable for the code to whatever we get from walking the state of the code. So here, if we look at walk later, it basically takes some line of code here. So we get our code from the state 2 and some substitution. So we get our substitution here from the state 2 as well. So we're keeping all this information that we got executing this code, but we're keeping it local. And basically that's the gist of it. Now there is some work to generate the constraints locally. And here we can see that L equal is just a later of equal. The expand annotations here are so that we generate, if we have L equal const 1, 2, const 1q, then we want to generate equal const 1, 2, const 1q, as opposed to generating equal 1, 2, 1, Q. So the expansion makes sure that we're actually doing this, recreating the const cells verbally as a const here in the generated code. And for CLP-SMT, the pattern is similar. We keep adding, accumulating the SMT commands into the state object. And when we do a Z assert, we accumulate, but we also check that the solver is still can still satisfy the answers. And it's only at the very end when we verify that we actually ask for the model of the solver. So I hope you had fun in this adventure, and hopefully it's the start of many more to come. So in terms of the code, the stageminicameron repo is here, and the CLP-SMT miniKanren repo is here. And I've also created those branches at ventralog on both fastminicameron and the canonical miniKanren, so that you can experiment with adding your own things to the state object. Okay, so that's it. Adventures in extending miniKanren. It was fun preparing this talk, and I hope you enjoyed listening. Thank you.